So hello everyone, welcome to this PDC lecture series. In this lecture, we will continue our discussion on frequency response analysis. So here we will highlight the key points of the this lecture. First, we will see the application of complex analysis, and in this section we will first introduce the complex number, and then we will highlight the properties of the complex number and the graphical as well as polar representation of the complex number and the De Moivre's theorem. Second, we will apply the complex number analysis to the complex systems, and we will try to plot the Bode diagrams for those systems. So here in the second point, we will see the Bode diagram for the first order system, 3 first order system in series, and for a control system. So now let's continue. So first, let's see the first point, that is complex analysis. So let's assume that we have a characteristics equation as following. S square plus 1 equal to 0. Let's say this is equation number 1, right? So to find the roots of this equation, we will have the plus minus under root of minus 1. So minus 1 is a negative number, and the square root is a function which is only defined for the positive number, right? So that's why here we have to use another term, I square. So where I equal to I is a iota, right? So I is an imaginary number which represents the square root of -1. So we will have s plus minus I as a root of equation number 1. Since control system, we generally use I for the current, so that's why in place of I we generally use J in the control system. To avoid the confusion between the current and the imaginary number. So in the next section we will use J as a imaginary number. So now we have J as a imaginary number, right? So for any complex number, complex number Z equal to for any complex number Z 1 equal to A1 plus JB. So for any complex numbers, Z1 is represented by A1 plus JB. Where the real part of Z1 is A1 and imaginary part of Z2 equal to B1. So here for any complex number, Z1 can be represented as A1 plus JB1. Let's say this is equation number 2. So the real part of Z1 equal to A1 and imaginary part of Z1 equal to B1. Now coming to the algebra of complex numbers. So property 1, z1 plus minus z2. The addition and subtraction of two complex number can be denoted as a1 plus j b1 plus minus a2 plus j b2. So therefore we will have a1 plus minus a2 plus j in bracket b1 plus minus b2. So it means we will have the summation of a I, where I goes from 1 to 2 plus j So this is the first property, right, and which can be further written as in the bracket the real part of z1 plus minus the real part of z2 then plus j times imaginary part of z1 plus minus imaginary part of z2, right. So the addition and subtraction of two complex number can be found as the property 2, the multiplication of two complex number, multiplication two complex number. So let's say we have two complex number z1 into z2, which can be written as a1 plus j b1 into a2 plus j b2 in the second bracket. So further simplifying, we will get a1 a2 minus b1 b2 plus j a2 b1 plus A1 B2. The property is number 3, division. So to find out Z inverse 1 upon Z1 can be written as 1 upon A1 plus J B1 so multiplying numerator and denominator by the conjugate of A1 plus J B1, that is A1 minus G B1. So we get A1 minus J B1 upon A1 square plus B1 square. And which can be written as the complex conjugate of Z1, that is Z1 bar upon the mod of Z1 whole square. Properties 4. The conjugate of a complex number. The conjugate of a complex number is the complex conjugate of Z1 is denoted by Z1 bar, and that is given as A1 minus J B1 if Z1 is A1 plus J B1. So if Z1 is A1 plus J B1, so Z1 bar will be equal to A1 minus J B1 by simply putting minus just before the J. So here we can see the real part of Z1 bar is also A1, that is real part of Z1. So imaginary part of Z1 bar equal to minus B1 that is minus imaginary part of z1 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 prime can be written as u1 plus j b1 in second bracket a1 minus j b1, and that is equal to a square minus j in bracket j b whole square, so which will further give us a square minus j square b square. J square is equal to minus 1, so that is plus b 1 square. So z1 into z1 bar equal to a1 square plus b1 square, and that is equal to mod of z1 whole square. So therefore z1 bar equal to mod of z1 whole square. P5, the modulus of complex number. So the modulus of a complex number is defined as z1 enclosed with square bracket enclosed with two line bracket equal to under root a1 square plus b1 square, and that is equal to square root of real part of z1 square plus imaginary part of z1 whole square. P6, so the polar representation the polar representation of complex number. The polar representation of a complex number is defined as so Z1 can be represented in the form of polar representation as the mod of Z1 into e to the power j theta. This is equation number 3. This is equation number 3. So where e to the power j theta is cos theta plus j sin theta, or sometimes it is also written as cis theta. C represents cos, I represent imaginary number, S represent sin, and that is cis theta equal to e to the power j theta, that is cos theta plus j sin theta. And this is known as Euler's formula. Euler's formula. So the graphical representation of Z1 is drawn. So the graphical representation of Z1 can be drawn in the complex plane. So in the complex plane we have imaginary axis and we have real axis. So in the complex plane we have real axis or imaginary axis. So the graphical representation of Z1, that is A1 plus J B1, can be shown this way. So move A1 distance in a real axis, and then move v1 distance perpendicular along the imaginary axis. So the corresponding point will represent a comma b1. So the point connecting origin to this point. So the line connecting origin to this point will represent the vector z1. So the vector representation of z1 can be seen as a vector which connects the origin to the point a comma b1, a1 comma b1, and this line will have the magnitude of z1 equal to mod z1 and the angle as theta. Let's say the point A represents a1 comma b1. So the distance of OA, line OA, will be mod of z1, and that will be the magnitude of z1, and the angle theta will be argument of z1, and that is represented by angle of z1. So this way we can represent any complex numbers in the complex plane by a polar form. So using these properties, we can find out the magnitude and the argument of any complex number. So the extension of this polar form can be further extended in properties P7. So in P7, so property P7, let z equal to z1 into z2. Therefore the mod of z will be equal to the mod of z1 and into the mod of z2, and this will be the equation number 4. And the argument of z will be equal to the argument of z1 plus the argument of z2. That will be equation number 5. So to prove this, we will use the polar form of E1, the polar form of Z1 and Z2. So let's assume Z1 equal to Z1 e to the power J theta 1 and Z2 equal to mod Z2 e to the power J theta 2. Therefore Z equal to Z1 into Z2 will be equal to Z1 into Z2 e to the power J theta 1 plus theta 2, and which can be further simplified as mod of z e to the power j theta. So comparing these two, we can say mod of z equal to mod of z1 mod of z2 and theta equal to theta 1 plus theta 2. So this is question number 6. So properties number 8, P8, de Moivre's theorem, according to which z1 to the power n equal to, in bracket r bracket open cos theta plus j sin theta bracket close to the power n equal to r to the power n cos in bracket n theta plus j sin in bracket n theta. So this is z1 to the power n according to the de Moivre's theorem. So all these properties we will further used to find out the stability analysis using the Bode diagram for the different types of linear systems. So let's move on to the next section. So the next section is Bode diagram. So the next section is Bode diagram. So let's start with the first order system. So let's assume we have a transfer function for first order g of s equal to Kp upon tau s plus 1, and that is given by equation number 1. So as we already know from the frequency response analysis, the amplitude ratio and the phase shift, these two parameters are required to get the frequency response of any linear system. So to find out amplitude ratio, first we need to put S equal to j omega into equation 1. So we will get g of j omega, and that will be equal to Kp upon tau j omega plus 1, and that is Kp 1 plus j omega tau. So if we see here, g omega is a complex number z, and which is in the form of 1 upon another complex number, that is 1 plus j omega, right? So this can be written as Kp 1 plus j omega tau whole inverse. And this is another complex number, that is, let's say z1. So to find out z1 inverse, we have to use the properties, and we know that z inverse can be written as 1 upon z1, and which will be equal to z1 bar upon z1 mod square. So using that property, we will have Kp z1 bar upon z1 mod square, and we can write this Kp, and the mod of z1 will be the real part of z1 square plus the imaginary part of z1 square. So this will be 1 square plus omega tau whole square, and z1 conjugate will be 1 minus j omega tau. So now we will find out the amplitude ratio. So the amplitude ratio is given by the mod of g of j omega, and that is equal to mod of z, and mod of z will be equal to kp 1 plus omega square tau square. Omega square tau square whole square plus minus omega tau 1 plus omega square tau square whole square root of this, and this will be equal to kp 1 plus omega square tau square under root. Similarly, the phase shift phi will be equal to the argument of z, that is argument of g of j omega, and that will be equal to tan inverse the imaginary part of z upon real part of z. The imaginary part of z is this one, and the real part of this is this one. So this is b and this is a. So this will be b upon a and finally we will have tan inverse in bracket minus omega tau kp upon 1 plus omega square tau square. This is the b term, imaginary part, and upon kp 1 plus omega square tau square. This is the real part. And hence phi will be equal to tan inverse minus omega tau. And the amplitude ratio will be equal to kp upon under root. So this is equation number 2, and this is equation number 3. So equation number 2 for the amplitude ratio, equation number 3 for the phase shift. So to plot the Bode diagram, so from equation number 2 and equation number 3, we can conclude that amplitude ratio and the phase shift both are the function of input frequency, that is omega. So to visualize how the amplitude ratio and the phase shift changes along the change in the frequency of the sinusoidal input, and the graphical representation of the plot which shows the amplitude ratio versus omega and phi versus omega is known as the Bode diagram. So taking the log of log 10 of equation 2, we will get log 10 AR equal to log 10 Kp upon under root 1 plus omega square tau square, and that will be equal to log 10 Kp minus plus log 10 1 plus omega square tau square whole square minus half, and further simplifying we will get log 10 AR minus log 10 Kp equal to log 10 1 plus omega square tau square minus half. So using the formula log a b to the power n equal to n log a b and log a n upon n equal to log a of m minus log a of n. So using these two formula we will have in the left hand side we will use log m minus log n. So we can write this as log 10 m upon n, that is AR upon Kp, and in the right hand side minus half log 10 1 plus omega square tau square. So this is the equation number 5 after taking the logarithm of the amplitude expression. So now we will see how to plot the log, we will see how to plot. So the next thing, we have to follow the certain rules to plot the Bode diagram. So the rule number 1, so to plot the Bode diagram, Bode plot, we will use certain rule, and that is rule number 1, find low frequency asymptote. So first find the low frequency asymptote by putting omega tends to 0. So when omega tends to 0, find the amplitude ratio or phase plot. Rule number 2, find high frequency asymptotes when omega tends to infinity, using both the expression for amplitude ratio as well as phase shift. And the third rule number 3, for the first order system, find out the corner frequency. So for find all corner frequencies, omega c. When omega tau tends to 1. So when find all corner frequencies when omega c when omega tau equal to 1, it means omega c will be equal to 1 by tau. So for a first order system, we will have omega c1 will be equal to 1 upon tau 1. So in case of 3 first order system in series, we will have 3 different corner frequencies, and which can be evaluated as omega 1 equal to 1 upon tau 1, omega 2 equal to 1 upon tau 2, and omega 3 equal to 1 upon tau 3, based on the time constant for the different types of first order systems. So once you know all these corner frequency and low frequency asymptote as well as high frequency asymptote, we can plot the Bode plot for the amplitude ratio as well as phase plot. So now let's start with the gain plot. Gain plot, and that is log 10 AR by Kp versus omega. So rule number 1, find out the low frequency asymptote. So when omega tends to 0, so when omega tends to 0, from the equation number 5, so when omega equal to 0, equation number 5 gives log 10 AR by Kp equal to minus half log 10 1 plus omega square tau square, omega square tau square, and this omega tends to 0. It means the second term becomes 0, and we will have this as 0. So finally this is y equal to 0 therefore AR by Kp will be equal to 10 to the power 0 equal to 1, right? So the low frequency asymptote start from 0, 1. So low frequency asymptote start with 1. So the next, following the next rule, so rule number 2, find high frequency asymptote. So when omega tends to infinity, so when omega tends to infinity, from equation number 5 we will have log 10 AR by Kp equal to minus half log 10. So if we see here in this expression, so log 10 AR by Kp equal to minus half log 10 1 plus omega square tau square. So when omega becomes infinity, so omega square tau square becomes very large. So we can neglect the first term. So we will have omega square and tau square, and finally we will get minus log log 10 omega tau. So here we have y equal to n x. So the slope of high asymptote, so the slope of high frequency asymptote m equal to -1. Now next, rule number 3. For a first order system, we have to find out the corner frequency. So to find out the corner frequency, so we have one first order system. So we will have when omega tau equal to 1. So when omega tau equal to 1, so from equation number 5, in that case, so from equation number 5, will be equal to y equal to minus half log 1 plus omega square tau square, and this omega tau is equal to 1. So we will have 1 plus 1, 2. So finally we have minus half log 10 2, and this will be equal to and so finally AR by KP will be equal to 0.707. So after solving this, so this will be at when omega equal to omega c. So when we have corner frequency, at that point the amplitude by Kp will be equal to 0.707. So using these three information, we will plot the gain plot. So Similarly, for phase plot, we will have phi versus omega, and again we have to follow all three rules. So when omega equal to when omega tends to 0, so in that case phi will be tan inverse minus omega tau, and this omega tau equal to 0. So we will have my tan inverse minus 0, and this will be equal to 0. So for rule number 2, when omega tends to infinity, so from equation number 3, so from equation number 3 we will have phi equal to tan inverse minus omega tau, and this omega tau equal to infinity. So this will be equal to tan inverse minus infinity, which can be written as minus tan inverse infinity, and tan inverse infinity is pi by 2, so this will becomes minus pi by 2 or minus 90 degree. So applying rule number 3 at the corner frequency, so when omega equal to omega c, in that case omega tau equal to 1. It means from equation 3 we will have phi equal to tan inverse minus omega tau, and omega tau equal to 1. So we have tan inverse minus 1, and that will be equal to minus tan inverse 1. So finally phi will be equal to minus 45 degree. So at corner frequency the phase shift will be minus 45 degree for the first order system. So now let's plot the Bode diagram. So in the Bode diagram we will have omega in the x-axis, and here we will have AR by KP. So first plot the AR by KP versus omega plot. So since we are plotting this on the log 10 versus log 10 scale, so we will have logarithmic 10 scales. So this is, let's say, 1, this is 10, this is 100, this is 0.1, and this is 0.01, 0.1, this is 1, this is 10. So at when omega is very low, omega tends to 0, it means AR upon KP equal to 1. So first we have to draw the low frequency asymptote. So this will be the low frequency asymptote L F A, which will pass through when AR upon KP equal to 1, right? So the next is high frequency asymptote when omega is very large. So in that case we will have the slope of -1, right? And so when omega tau is equal to 1, it means the corner frequency will be equal to 1 by tau, and this will depend on the system parameter, so 1 upon tau. So first we have to identify what is corner frequency. So let's say my corner frequency is here, right? So this is omega c. So at this point the high frequency asymptote as well as low frequency asymptote will cut each other, right? So at this point, if we extend a vertical line, so at this point we will have the intersection of low frequency asymptote to the high frequency asymptote, and since we already know for a unit change in y, we will be having unit change in x. For the high frequency asymptote, so we will have a high frequency asymptote which will have -1 slope. So basically so here we will have 1 by 1. So this will be 1 unit, so this will be 1 unit, right? So the slope will be -1. So the for high frequency asymptote we will have -1 slope. So this will be high frequency asymptote. So at the corner frequency, the value of so AR upon Kp at the corner frequency equal to 0.707. So 707 will be somewhere here. So now we can draw the gain plot in this way. So similarly, to plot the phase plot, again we have to so this is omega and this is, let's say, phi. So when omega equal to 0, we will have low frequency asymptote at 0 degree. So this will be your low frequency asymptote. So low frequency asymptote. So when omega tends to infinity, we will be having minus 90. So at high frequency, when omega equal to infinity, we will be having minus 90 degree. So we will be having minus 90 degree. So this will be the high frequency asymptote. And when so at this corner frequency, the phase shift will be minus 45 degree. So it means we can plot the phase shift diagram like this. So this is the Bode diagram for first order system, and this is the figure. So this is Bode plot for Kp upon tau s plus 1. So that's all for today. Thank you for your attention.